Picture this. It's 1965, and you're standing in a Texas machine shop watching $15,000 worth of racing engine literally eat itself alive. Metal shavings glitter in the oil pan like gold dust, except this dust means you're out of the race and out of money. The engine? A Chrysler 426 Hemi, the most dominant racing power plant ever created. The problem? Nobody could keep them alive past 50 passes down the quarter mile. Not even Chrysler knew why their legendary elephant motor kept destroying its own camshaft bearings at high RPM. Then a soft-spoken mechanic named Keith Black picked up a drill, made 5 tiny holes, and solved a problem that had the best engineers in Detroit scratching their heads. This is the story of how one Texas mechanic discovered something Chrysler's entire engineering department missed: a fatal flaw in the Hemi's oiling system that only appeared above 8,000 RPM. His fix was so simple it seemed impossible, so elegant it made trained engineers feel stupid, and so effective that every serious Hemi racer in America would eventually drill those same 5 holes in their $15,000 engines. Let me take you back to the mid-1960s, when drag racing was exploding across America, and the Ford 26 Hemi was the undisputed king of the quarter mile. Chrysler had released this monster in 1964, and on paper, it was perfect. Dual 4-barrel carburetors, hemispherical combustion chambers that allowed massive valves and optimal flame propagation, forged steel crankshaft, cross-bolted main bearing caps. The street version made 425 horsepower, though everyone knew that was a lie to keep the insurance companies happy. The race version? We're talking 550 horsepower naturally aspirated, with some builders pushing 700 on nitromethane. The architecture was revolutionary. Those hemispherical heads weren't just marketing, they represented the ideal combustion chamber shape. The valves could be huge, 2.25-inch intakes and 1.94-inch exhausts, because they sat at opposing angles instead of inline like conventional wedge designs. The spark plug sat dead center in the dome, giving perfect flame travel in all directions. The ports were straight and unobstructed. Air and fuel flowed like water through a fire hose. But here's where things got interesting. And by interesting, I mean expensive. Drag racers quickly discovered the Hemi had an appetite for self-destruction that matched its appetite for quarter-mile records. Build a Hemi to racing specs: high-lift cam, solid lifters, valve springs that could bench press a small car, and it would run like a scalded cat for about 50 passes. Then you'd hear it. That sickening metallic knock that meant your cam bearings had welded themselves to the camshaft. Pull the engine apart, and you'd find carnage. The cam journals scored and blued from heat, the bearings spun in their bores, metal particles throughout the oil system like someone had added a tablespoon of glitter to your oil pan. The damage pattern was always identical. The number 2 and 4 cam bearings, the ones in the middle of the block, failed first. They'd lose oil pressure, overheat, and essentially spot weld themselves to the spinning camshaft. Once they spun in their bores, oil pressure dropped to nothing, and the engine was toast. We're talking about complete rebuilds: new camshaft at $400, new bearings at $150, machine work to repair the damaged bearing bores at $500, plus labor, plus lost race weekends, plus watching your competition collect winners' purses while you collected parts invoices. Chrysler's response? They insisted the engine was designed correctly. The Hemi's oiling system was a priority main system, meaning oil went to the main bearings first, then through passages to the cam bearings, then to the top end. On the street, it worked perfectly. The engineers at Highland Park had tested these engines extensively, but they'd tested them at street RPM, maybe 6,000 on a bad day. They never anticipated what drag racers would do to their creation. See, competitive super stock racers were spinning these engines to 7,500, 8,000, sometimes 8,500 RPM through the traps. At those speeds, the physics of oil flow change dramatically. Centrifugal force becomes a major player. Oil that should flow through carefully designed passages gets flung outward. Pressure drops in some areas while building in others. The carefully balanced system that worked at 5,000 RPM became a time bomb at 8,000. Enter Keith Black. Black wasn't a trained engineer. He didn't have a degree from MIT or years at Chrysler Tech Center. What he had was a machine shop in Texas, a reputation for building winning engines, and the unfortunate experience of rebuilding dozens of wounded Hemis. Every failed engine told him the same story. Those center cam bearings were starving for oil at high RPM. Black studied the Hemi's oiling system like a detective studying a crime scene. Oil entered the block through the oil filter, traveled through the main oil gallery, then fed the 5 main bearings through passages drilled from the gallery. From each main bearing, oil was supposed to travel up through the main bearing saddles to reach the cam bearings above. But here's what Black noticed. The passages from the mains to the cam bearings weren't straight shots. They had to navigate around webbing, through narrow channels, making multiple direction changes. At street RPM, oil had time to make those turns. At 8,000 RPM, with the crankshaft whipping oil into a hurricane inside the crankcase, those passages couldn't flow enough oil to keep the cam bearings alive. The number 2 and 4 bearings, being furthest from the oil pump and having the most convoluted feed passages, died first. Every single time. Black's solution was so simple that when he first explained it to other racers, they thought he was joking. He drilled holes, 5 of them. One 1/8-inch hole in each main bearing saddle, creating a direct oil feed from the main oil gallery to the cam bearing above. No complex passages, no direction changes, just a straight shot from the high-pressure oil gallery directly to where it was needed. The modification took 30 minutes with a drill press and cost literally nothing if you already owned the drill bit. But would it work? The first test engine was a full-race 426, built for a local superstock competitor, 12-to-1 compression, radical solid cam with over 0.600-inch lift, valve springs with 350 pounds of seat pressure, the kind of build that usually needed cam bearings every 50 runs. Black drilled his 5 holes, assembled the engine, and sent it to the track. 50 passes. No problems. 100 passes. Still perfect. 200 passes. The racer pulled the valve covers expecting to find wear, damage, something. Instead, he found clean oil and cam bearings that looked barely broken in. Word spread through the Texas drag racing community like wildfire. Keith Black had figured out something Chrysler couldn't or wouldn't. Racers started showing up at his shop with wounded Hemis, and Black would perform his modification. The results were consistent. Engines that previously ate cam bearings like candy now ran entire seasons without failure. But here's where it gets really interesting. When word reached Chrysler about Black's modification, you'd expect them to either dismiss it or quickly adopt it. Instead, they sent engineers to Texas to study what this mechanic had discovered. The engineers confirmed what Black already knew. At sustained high RPM, the stock oiling system simply couldn't deliver enough volume to the cam bearings. Black's direct feed holes solved the problem elegantly. So why hadn't Chrysler's engineers discovered this during development? Simple. They'd never tested sustained operation above 7,000 RPM. The Hemi was designed as a street engine that could go racing, not a race engine that could drive on the street. The factory's priority main oiling system was actually superior for street use. It ensured the bottom end always had oil, even during low-speed operation or when oil levels were marginal. Black's modification worked for racing, but could actually cause problems on the street by reducing oil pressure to the mains at idle. The technical details of Black's modification reveal its genius. Those 5 1/8-inch holes had to be precisely located. Too high, and they'd miss the oil gallery. Too low, and they'd weaken the main bearing saddles. The angle mattered too. Straight vertical holes worked, but a slight angle toward the cam bearing improved flow. Black even discovered that chamfering the holes on both ends reduced turbulence and improved flow by about 10%. The modification addressed several problems simultaneously. First, it provided direct high-pressure oil to each cam bearing. Second, it actually helped cool the cam bearings by increasing oil flow rate. Third, it prevented the oil starvation that occurred when the engine was under heavy acceleration and oil was forced to the back of the pan. Fourth, it eliminated the pressure drop that occurred in the stock passages at high RPM. Black didn't stop there. He developed a complete oiling system modification package for the Hemi. Enlarged oil passages to the rockers, grooved cam bearings for better oil distribution, external oil lines to supplement the stock system, high-volume oil pumps with reinforced housings, deep sump oil pans with trapdoors to prevent starvation under acceleration. Each modification addressed a specific weakness he'd identified through careful observation of failed engines. The impact on Hemi performance was immediate and dramatic. Engines built with Black's modifications could sustain 8,500 RPM indefinitely. Some radical builds pushed 9,000 RPM, speeds that would have destroyed a stock oiling system in seconds. Reliability improved so dramatically that racers could focus on going faster instead of rebuilding engines. ETs dropped, speed records fell. Black-built Hemis started dominating superstock and pro stock categories nationwide. By 1967, Keith Black had become the most famous Hemi builder in America. His shop in Texas was booked months in advance. He was building engines for the biggest names in drag racing: Don Garlits, Sox and Martin, Grumpy Jenkins. When someone wanted a bulletproof Hemi that could survive the punishment of professional drag racing, they went to Keith Black. The success led Black to develop his own aftermarket parts. He designed aluminum Hemi heads that flowed better than stock while weighing 50 pounds less. He created his own line of forged pistons specifically designed for nitromethane racing. He developed billet aluminum Hemi blocks that could handle over 2,000 horsepower. Every product incorporated lessons learned from fixing Chrysler's original design. What made Black's approach revolutionary wasn't just the technical innovation, it was his methodology. While Chrysler's engineers relied on theory and controlled testing, Black learned from failure. Every wounded engine that came through his shop was a teacher. Every failure pattern revealed a weakness. Every successful modification proved a theory. He turned his machine shop into a real-world laboratory where engines were pushed beyond their limits and solutions were developed through trial and error. The relationship between Black and Chrysler remained complex. They couldn't officially endorse modifications that might void warranties or create liability issues. But behind the scenes, Chrysler engineers studied Black's work carefully. When they developed the second-generation Hemi in the 2000s, it incorporated several oiling system improvements that addressed the exact problems Black had identified 40 years earlier. Consider the numbers for a moment. A properly built race Hemi in 1965 cost about $15,000. That's $140,000 in today's money. Cam bearing failure meant a teardown and rebuild costing $2,000 minimum. A competitive superstock racer might make 200 passes per season. Without Black's modification, that meant 4 rebuilds per year at $8,000 total. With his modification, maybe 1 rebuild for regular maintenance. The 5 holes Black drilled saved racers thousands of dollars and countless lost weekends. But the real impact went beyond money. Black's modification kept engines alive long enough for racers to push other boundaries. With reliable oiling, they could experiment with wilder camshafts, higher compression, more aggressive tuning. The Hemi's true potential could finally be explored. Power levels that seemed impossible in 1965 became routine by 1970, partly because engines could survive long enough to be properly developed. The modification technique spread throughout the racing world. Other engine builders began applying similar thinking to different engines. Direct oiling became standard practice in professional racing. The idea that factory engineering might have room for improvement became accepted wisdom. The racing community learned that sometimes the best solutions came not from engineering degrees, but from careful observation and practical experience. Black's influence extended to modern engine design. Today's high-performance engines routinely feature piston oil squirters, priority main oiling, and direct feed passages to critical bearings, all concepts that Black helped pioneer through practical modification of existing designs. Modern racing engines can sustain RPM levels that would have seemed like science fiction in 1965, partly because of oiling system improvements that trace back to a Texas machine shop. The story also highlights a fundamental tension in automotive engineering. Street engines and race engines have different requirements, different duty cycles, different failure modes. What works perfectly at 3,000 RPM might fail catastrophically at 8,000 RPM. What's optimal for a 100,000-mile warranty might be completely wrong for a 10-second quarter-mile pass. Black understood this intuitively. He wasn't saying Chrysler's engineers were wrong. They'd designed an excellent street engine. He was adapting their design for a completely different application. Think about the elegance of the solution. No exotic materials, no complex machining, no expensive parts, just 5 holes drilled in exactly the right places. It's the kind of modification that seems obvious in retrospect, but required deep understanding to discover. Black had to understand not just what was failing, but why. He had to trace the failure back through the oiling system to find the root cause. Then he had to devise a solution that addressed the problem without creating new ones. The modification is still used today. Walk into any shop building vintage Hemis for drag racing, and you'll find those 5 holes. They're drilled with the same careful precision Black specified. Same diameter, same location, same angle. The modification has been refined over the decades. Some builders add additional holes or enlarge certain passages, but the fundamental concept remains unchanged. Direct feed to the cam bearings, simple, effective, bulletproof. Keith Black passed away in 1991, but his legacy lives on in every properly built Hemi. His company, Keith Black Racing Engines, still produces high-performance parts based on his designs. His aluminum Hemi heads are considered some of the best ever made. His forged pistons are found in championship-winning engines worldwide. But perhaps his greatest contribution was proving that innovation doesn't always come from corporate engineering departments. Sometimes it comes from a guy with a drill press who's tired of fixing the same problem over and over. The story resonates because it's fundamentally about problem solving. Black faced a challenge that was costing racers money and championships. He studied the problem systematically. He developed a hypothesis. He tested it. When it worked, he refined it. Then he shared it with the community. No patents, no trade secrets, just a simple modification that anyone could perform. That openness, that willingness to share knowledge transformed drag racing. Modern engineering has become incredibly sophisticated. Computer simulations can model oil flow down to the molecular level. Pressure sensors can map exactly what's happening inside an engine at any RPM. But Black's modification reminds us that sometimes the best solutions are simple. Sometimes observation beats simulation. Sometimes practical experience trumps theoretical knowledge. Sometimes a mechanic with a drill can outsmart an entire engineering department. Today, when someone builds a max-effort Hemi for drag racing, those 5 holes are drilled before the engine is even assembled. It's become such standard practice that many builders don't even know why they're doing it. They just know it works. That's Keith Black's legacy, a modification so effective it became invisible, so essential it became automatic. The next time you see a vintage Hemi screaming down the quarter mile at 8,000 RPM, Remember those 5 little holes. Remember the Texas mechanic who figured out what Chrysler missed. Remember that sometimes the difference between success and failure, between winning and watching your engine destroy itself, comes down to 1/8 of an inch of drilled aluminum and the wisdom to know where to put it. What's the most elegant engineering solution you've ever seen? Something so simple, it made you wonder why nobody thought of it sooner? Drop it in the comments below. And if you enjoyed this deep dive into drag racing history and engineering problem solving, hit that subscribe button for more stories of innovation, determination, and the people who refuse to accept that something can't be fixed. Until next time, keep those engines running, and remember, sometimes the best solution is the simplest one.